Yes, so now let us give a sketch of proof. So of the statement that we stated in a few slides ago. So we take F Fermat hypersurface of degree delta, and so we suppose that delta is larger than n+1 times n minus p. And we take a non-degenerate holomorphic map from CP to F. So we lift it to the projective space. No, we lift it to, Cn+1, as it takes value in the projective space. Write it in the following fashion, and we can always suppose that f0 0 is not equal to 0, and that f is non-degenerate at 0, because we suppose that the map was not degenerate. So up to translation, we can suppose that it's at 0. And so we will denote for U a full set, so of size big N minus 1, PU, so the following operator. So we take this N global section of O delta, and we restrict it to F. So it gives a global section of this vector bundle with this positive twist. And so I recall for people maybe not so familiar with algebraic geometry that there is a tautological very ample bundle of Pn, which is O1. So the global section of O1 are simply the linear polynomials, and more generally, the global section of OD are the homogeneous polynomial of the grid. And so the goal here is to prove that PU evaluated on F is identically 0 for every full set of size big N minus 1. So if we are able to do so, then by the fundamental property of Wronskian, we deduce that so there is a linear combination, so between the n last coordinates of this map elevated to the power delta, that is equal to 0. And so this will give the equation of the other Fermat hypersurface in which the image of the map F lies. So here we really use we use the fundamental property of geometric generalized Wronskian in its strong form. So first we are going to distinguish between two cases. So the first case is we take full sets that do not contain a letter, say I between 1 and p. So here the fact that f is non-degenerate at 0 implies that, well, we can, up to reparameterizing the source, we can locally simplify f. And so we can write it in the following fashion. So where the first coordinate simply is n1 and p, so of course up to reparameterization of the variables. And the last coordinates are gp plus 1 gn, where gi is fi divided by f0, composed with the local holomorphism. And so now we just write locally what we find with our very definition of Wronskians. So what we find is the following. So we have the determinant of this matrix. So observe that here on the is column, since the full set does not contain the letter I, we obtain 0 here because we differentiate according to variables, well, that is not zi, so we always obtain 0. And so for the last column, so here we use a combination between the column to make appear this last column. And actually, since we know that the F lands in the Fermat hypersurface, we know that this equality holds. So here, gi for y between 1 and p is simply z1 and p. And so here, this is because the image of F lands in the Fermat hypersurface. And so we can do this. So we replace the last column with this sum. And so we obtain -1 and 0, 0, 0. Of course, by antilinearity of the determinant, and so still by antilinearity of the determinant, this must be identically 0. So this settles, so this case, a very particular case. So the second case is the other full sets. And so in this case, observe that so Ku is by definition the maximal length of a word in the set U. And observe here that the maximal length of a word in so the other full set U must be less or equal than n minus p. So why is that so? Well, since we suppose that it contains all the letters, we must have 1, 2, and p. And since also we ask that the set is full, well, to keep a full set and obtain a set with an element in it that is of maximal length, so here this is the best possible way to do so. And so this is why we find that the length of a word inside the other use is at most n minus p. So that being said, observe that so the definition of our Wronskian is that, well, we differentiate here, so local sections, and here these sections are only powers. So if we do not differentiate them that much, then we will have a factorization. And so here we have, for this reason that we do not differentiate that much, already this factorization. And so here the twist is still positive, but less positive. And to obtain a negative twist, here, well, we use the fact that we are on a Fermat hypersurface, and we use this equality. And so we can make appear a further factorization by x0 here. And so now this section takes value in this vector bundle, and with our hypothesis, this twist is strictly negative. And so we can then use the vanishing theorem to conclude the proof of the result. So basically, really, this is very specific to the fact that we are on a Fermat hypersurface, allowing to obtain really already here very nice factorization, still not enough to have something negative, but then with this equality, we can obtain something negative, and then use the general vanishing theorem, allowing to conclude what we wanted. Okay, so this is it for the first application of geometric generalized Wronskian to hyperbolicity. And now I will discuss about two applications to foliation theory. So for the first application, we are going to use a very specific Wronskian. So what is the specific Wronskian? So it's the following. So you take n, a natural number, and we denote by un the set of, so in this set, we put all the words of length less or equal than n here. So of course, as we put all the words, it is a full set. And so we'll denote by m its cardinality. So as I said, since un is a full set, the pure generalized Wronskian associated to it is geometric. So I recall that, so it satisfies this functional property, so this, say, homogeneity property. But it has a further very nice property, which is the following, that if you let the group of holomorphism of CP0 act on it, then actually we recover the same Wronskian with a constant that is the determinant of the differential of our holomorphism, 0 elevated to a certain power. And so, well, to show that kind of property, first one has to see that when we do apply such a holomorphism, we recover a constant time, this this same Wronskian. Then one has to see that this constant does actually only depends on the first derivatives of psi. And then one can conclude with representation theory, as then we have a polynomial one-dimensional representation of the general linear group. So it must be a power of the determinant. So one does not have to do the computations. So well, this is roughly the idea to prove that. Now, how can we apply that this specific Wronskian to foliation? So first, I'm going to recall what is foliation in the regular case on the manifold. So we take X a projective manifold of dimension big N, and foliation of rank P is the data of distribution of P plane, so equivalently a subvector bundle of Tx of rank P, which means that for every point in X, the fiber of the foliation of the foliation at X is a subvector space of the tangent space of X, and you require that it varies holomorphically with X. So this is what is a holomorphic distribution of P-plane. And for it to be a foliation, one has to add another condition, and this condition is that it must be locally integrable. So usually one says that it is an involutive distribution, which is due to Frobenius theorem. And so what does it mean to be locally integrable? It means that around every point of the projective manifold, one can find a small open set on which there exists a biholomorphism of the following form. So we've written it in this form, and we require that it has to be adapted to the foliation in the following sense, that if you differentiate this map according to the variable z, and apply it to the tangent space at z of Cp, then you recover your foliation at this point. And so, well, said otherwise, this trivialization is local integration of our foliation, since when we differentiate it, we recover the foliation. So this is why, in this sense, we say that it is locally integrable. So this is for the definition of a foliation of rank P. And by seeing how it behaves locally. And so, of course, the data of the foliation is going to be given by the transition functions on the foliation. And so here, a change of trivializing chart will be given by a family of biholomorphism of this following form. So it has to, so the first coordinate must depend only on W, and the second is depend on W and Z, and it has to be of this form so that it respects these properties. Okay, so this is for the quick definition of a foliation in the case of manifolds, when the foliation is regular. And now we'd like to apply Wronskians to foliation, and let us explain how to do so. And how to apply our very specific function in this case. So we fix L an amperland bundle, and we fix global section over. So as before in the case of in the setting of hyperbolicity. And so the idea is to evaluate this operator at a local integration of f around x, which means that we would like to consider this number. So here the sections have been written in a local trivialization, and so here we have, if we fix the variable w, we have really mapped from Cp to C that we can differentiate according to the words in our full set UN and evaluate it in 0, 0. And so here, this number depends both on the choice of trivialization for the line bundle, so how we write our section in trivialization, and it depends as well on the choice of trivialization of the foliation. here. So to make it, so for it to be define something interesting, one has to really understand how this number behaves by change of trivialization. And actually, we do know, with the two properties we enunciated, how it behaves. So if we change trivialization for the line bundles, well, we've already seen it in the case of the application in hyperbolicity, we multiply this number by this transition function of the line bundle. And in the case of the change of trivialization of the foliation, the foliated variety, it changed by the multiplication by the determinant of the differential of the change of foliated coordinates to the power alpha n. And so all of this allows to show that this local definition actually allows to construct a global section, so of this line bundle. So here for the L to the power m plus 1, this comes from it. And here, well, you can take it as a definition of the canonical bundle of the foliation. This is
This est une compilation des Jungle Bros.
Pardon, sorry. So this is
This est une compilation.
So, okay. Sorry, I have a problem with Siri, which I don't know why it does that. Okay, so it allows to construct a global section of this. So I've explained this factor. For this one, you can take the canonical bundle KF to be defined by saying that it's given by trivializing the data of the trivialization of the variety and the change of charge given by the determinant of the differential. It's a way to define the canonical bundle of a foliation, which actually is as important, I mean, the foliated case as the canonical bundle of a variety, which is the determinant of the cotangent bundle. Okay, so this is the idea.
This est une compilation des Jungle Brothers, sortie le 13 septembre 2005.
Okay, so it's okay. Okay, so this construction allows to show the following. So if you take a X projective manifold, F a regular foliation around P on it, L an amperline bundle on it, and so here we will denote by epsilon tilde the global tilde Caesar constant of L. So I will not define it, so it's not really important. This is a constant associated to the line bundle. It's a measure of its. So we know that an amperline bundle is positive by definition, but it's a measure of how positive it is in some sense. Then the conclusion is that the line bundle Kf plus P plus 1 divided by epsilon tilde L is nef. So nef means by definition that its intersection number with any curve is positive. So said otherwise, if you take your canonical bundle restricted to F, so it's a line bundle of a curve, so you can take the degree. The same for L, and so you ask that this condition holds. So this is what it means to be nef, that this condition holds for any curve, any irreducible curve. Okay, and so to prove that kind of result, the idea is, well, with the previous construction, to construct global section of big power of this that do not vanish at any given point. And so actually, so I will not enter the detail because it's a bit here technical, and I just would like to emphasize simply on the idea on how we can construct them via the previous method. Then here one only has to check some details as to what kind of section we produce and how can we ensure that it does not vanish. But here this is mainly technicals, and this is where this constant actually naturally appears. that kind of construction allows to show these types of results. So it's with the Wronskian method, we can construct sections and we can have some control of them, and it allows to show some global statement as these ones that we can have the nefness of such canonical bundles with an additional positive line bundle. So this is for the first application to foliation theory. And as a last application, I'd like to discuss the integrability criterion of leaves of a foliation. So what is a leaf of a foliation? So by definition, it is an integral analytic submanifold with dimension P defined by the foliation. So what do we mean by that? I'll go back a bit backwards. So here you have this trivialization. So if you fix W, you can locally see this as a map only depending on Z, and it will give a local analytic submanifold of dimension P only on the trivializing chart. And so say you have this, then you take another point, you take another trivializing chart, and you try to extend your analytic submanifold of dimension P, and you do that until you exhausted all your open set, say, and so this will be a leaf of the foliation. And so fundamental theorem due to this contribution due to Bogomolov, McQuillan, Bost, Campanapon, and Druel is the following. So if you take a projective normal variety, so say normal for it's not a smooth variety, so you allow say singularities in codimension 2. And if you take F a foliation of rank P on this projective normal variety, so not necessarily regular, and an ample line bundle on X, then if the Zariski closure of a general leaf of F is not an algebraic variety of dimension P, then the conclusion is that there exist infinitely many Mn with coefficient tending to 0, such that the space of global section of the reflexive symmetric powers of the cotangent bundle F, so to the nth reflexive symmetric power of the cotangent bundle times the mth power of L, then the space of global section of this vector bundle is this reflexive sheaf is not 0. So, well, I will not define.
Why it is reflexive?
Well, it's by definition. I will not define what it means, but here, say you take the how do you define that? So you take the symmetric, the n symmetric power, and then you take its dual and its double dual, and so it becomes reflexive. So this, by definition, is the double dual of the nth symmetric power of the cotangent bundle of F.
So it is locally free in codimension 2, right?
Yes.
Okay.
Okay, so and this state, so in this case, we say that the cotangent bundle of the foliation is pseudo-effective, and so basically, this gives a criterion for the leaf to be algebraic, because if we show that this is always 0 for this, then the leaf has to be algebraic. So this is usually how it is used. And so with Wronskian methods, so using the same kind of ideas that we say describe explicitly with the case of a specific Wronskian, we can show the following. So same setting as before, take a projective normal variety, a foliation of rank P, an ample bundle. Same hypothesis, if the Zariski closure of a general leaf is not algebraic, then one can show that this locally free sheaf, so this twisted locally free sheaf, that has a global section. And so here it's the reflexive and tensor power. And so, well, and in some applications, it's sometimes enough to know that.
Okay. So you say that if this condition is satisfied,
Yes.
so it is a definition of pseudo-effective vector bundle, right?
This, no.
So can you back in the previous page?
It has to be the symmetric.
So one says that the cotangent bundle is pseudo-effective.
If this
So,
holds, yes.
Okay, so if this condition is satisfied, you say that this vector bundle, the cotangent bundle, is pseudo-effective.
Exactly.
Okay, so.
And so here it's about reflexive symmetric powers, whereas actually with Wronskian method.
So, and L is fixed or L any ample line bundle?
L is any ample line bundle. I mean, if it holds for ones, it holds for any. If this condition holds for ones, it holds for any.
Okay.
So it does not. I mean, the notion.
Okay, so if this cotangent bundle is just line bundle, so if X is projective curve, okay. So I mean, is it a good definition of
yeah, this is
pseudo-effective line bundle?
Yes, this is you recovered. I mean, the characterization of the pseudo-activity of a line.
So is it okay? It is a cohomological characterization. Okay.
Yes. And so, well, of course, here's in the case of foliation of Wronskians, this is the same statement than the previous one, because the tensor product and symmetric product are the same in this case. But here the conclusion is weaker, because we can, I mean, with Wronskian method, we can construct actually section of Schur powers of this, but we cannot ensure what kind of Schur power appears. So it should be the symmetric ones, but we are not able to prove it. So it's just about the statement is just about the tensor power. And so once again, this is mainly technical to prove that. So I will not enter into the details, but I will just hope that it's clear by now how one uses Wronskians really to construct a global section of some object of certain kinds, and then, well, one has to work a bit to obtain some precise information, which depends on the geometry of the variety we are dealing with. But yeah, I will not enter the detail, and I think I will stop here, and I'm glad to answer any question.
Yeah. So I didn't see this definition of pseudo-effective vector bundle. So you found it in the MIE lecture, or?
Yeah, it's not the same. It's quite recent actually. So it's not.
Okay.
It's a different definition.
So and it depends on foliation, right? So this definition depends on the foliation and on the foliation of.
No, you could take it as a definition. You replace foliation by a vector bundle, and you could take it as a definition of pseudo-effectivity of vector bundle.
Okay, so there are some notion of effective vector bundle. So yeah. For line bundle there are this notion, but for effective for vector bundle, yeah, I don't know how we can define effective vector bundle. Well, because you know that pseudo-effective is a limit of effective.
Yes, but so if for me, effective vector bundle is so here. So here we have to take this artifice, the reflexive, because this is not a vector model. It's so when one has to
yeah, it's coherent shape, which is reflexive. I see.
So suppose that it is a vector bundle. That being effective only means that the symmetric power of the vector bundle has a certain symmetric power as a global section. I think this is
Okay.
This is the definition of effectivity. And so it's on sense here. This is
so in which lecture of the MIE I can find this definition of pseudo-effective?
You will not find it in the MIE. I mean,
okay. So
you will find it in the paper of Druel, when where he extends the Boville-Bogomolov decomposition in some singular cases, and so it was quite recent. So I think 4 or 5 years ago, and so this is where I actually first saw it. But I do not have them here, but I can give you the reference.
Okay. Yes. Because I know some characterization of a cohomological characterization of pseudo-effective line bundle. So I think I forget the name of this guy. So he is I think he's Chinese, so works in Nice University.
Wow.
He's student of the MIE. Do you know? Yeah, Julian Sao. Yeah. So I think he gives the characterization of pseudo-effective, cohomological characterization of pseudo-effective line bundle. But this characterization of pseudo-effective vector bundle is new for me.
But okay, so